I want you to try out a question where a block is sliding down an inclined plane and there is no friction anywhere. It seems simple, and when you try out, you try to see what are the answers that you are going to arrive at for this particular question. In fact, it is a simple question only, where you need to apply energy conservation and solve the question. So I'll share the question on the screen, have a look at it and try to attempt it on your own. In this question, students kind of end up making small mistake points, which see if you are avoiding it, and if you're avoiding it, that's really good. If not, you can learn that small points where students generally tend to make mistakes. So I'll share the question on the screen. First, you must try this question out, especially if you're like an aspirant who's going to be appearing in 2023. This is definitely a must try on your own, right? So I'll just share the question. Do try it out. So here is it. You have an arrangement of two moving objects. There is a small block of mass m and there is a wedge having the same mass as that of the block. Inclination of that inclined wedge is given to be theta, and the wedge is placed on a fixed floor which is smooth and there is no friction anywhere. Height of the wedge is given to be h, and the question says the system is released from rest. So the block is going to slide down along the wedge and reach the bottom. You are asked to find what will be the velocity of the wedge when the block has reached the bottom, and you have to express your answer in terms of the parameters that are given. So height of the wedge and theta, and of course g, you can keep it as g itself, don't substitute g as 10, and see what answer you are going to land up with for this particular question. Before you take on my discussion, make sure you have tried it out on your own first. Yeah, so hopefully now you have tried it out. Let's see what happens in this particular question. So here is the first mistake which should be avoided. Of course, the wedge is going to be moving towards left. So when the block has reached the bottom, let's say the wedge has some velocity v1, and mistake number one is assuming that the velocity of the block with respect to ground is going to be down the wedge. Now, if you have avoided this mistake, it's good. Let's see what are the further mistakes which could have happened in this particular question. See, first of all, understand why with respect to ground, this block will not have a velocity down the plane. So as seen by ground observer, so imagine that after some time, this particular wedge has moved to the left. Originally, the block was at, let's say, point 1. Now it would have, it is of course sliding down along the plane, but it would have reached a point somewhere over there, point 2, sometime later. So velocity of this sliding object, as seen by ground observer, note that it is not along the inclined face. So as seen by ground observer, the velocity of this sliding object is in some direction which we cannot directly predict. Right. So this is point number one. If you have identified this, that's good. Then the next kind of mistake which can happen, you would have identified, yes, the velocity of the block is not down the wedge, but you made mistakes in writing momentum conservation. That is, you wrote mv1, which is momentum of the wedge towards left. Applying momentum conservation is right in the horizontal direction, obviously, because in the horizontal direction on this system there is no external force, but you have to be careful while writing that equation. So a mistake that can happen is writing mv1 equal to m times v2's component in the horizontal direction over there will be v2 cos theta. That is because the inclined plane with the horizontal will make angle theta like that. So v2's component along the horizontal is going to be v2 cos theta. And if you write mv1 cos theta equal to mv2 cos theta, now this is obviously not a correct relation. And one more mistake which could have happened is writing mgh, the drop in potential energy of the block which is sliding down, that will be gain in kinetic energy of the system. So writing it as half m v1 square plus half m v2 square. This relation is also not a correct relation. So if you had made mistakes in one of these two equations or in both equations, it's time to rectify that properly. See what are the correct ways of approach. So one of the ways to approach this particular question would be to take something of this sort. I'll just present it to you. See, here be very careful. Of course, the wedge is going to have some velocity. I'm calling it as v1. With respect to an observer on the wedge, this block will be sliding down. as seen by observer on the wedge. That velocity I'm taking it as v2. So as seen by ground observer, you vectorially add velocity of the wedge, you will get vector addition of v1 and v2 will be velocity of the block with respect to ground observer. Then now we write momentum conservation with respect to ground. So the momentum of the wedge mv1 towards left, that will be equal to momentum of this block towards the right, which is going to be now velocity of the block towards right should be v2 cos theta minus v1. So momentum of this particular block in the horizontal direction. So carefully note how we wrote momentum conservation equation. And also while writing energy conservation equation, the kinetic energy of this block which is sliding down will be speed square. So if I have to get the speed of this moving block in terms of v1 and v2, note that these are the two vector velocity components. So v1 and v2, when you vectorially add, you are going to get the speed, and the angle between these two vectors will be 180 minus theta. So speed will be root of v1 square plus v2 square plus 2 v1 v2 cos of 180 minus theta. So that will be speed. Now when we square it, we can write the kinetic energy of the block as this expression v1 square plus v2 square minus 2 v1 v2 cos theta, because cos of 180 minus theta is going to become minus cos theta. Now from these two equations, we need to solve for v1. So what you do, from equation number 1, you get v2 in terms of v1 and put it in the second equation. Wherever v2 appears, you replace it with v1 and solve for v1. You are going to get this expression v1 equal to root of gh divided by secant square theta plus tan square theta. So this is one of the ways of approaching the question. Now there is yet another way in which you can assume the variables. Now instead of assuming velocity for the block as seen by an observer on the wedge, so what I'm going to be doing, get another approach. This is absolutely fine, this approach that if you make use of with respect to an observer on the wedge and then adding the velocity of the wedge to get velocity of the block with respect to ground. So that is vector addition of v1 and v2. Now what I'm going to do is a different mm, way of assuming the vectors. So I'm assuming now as the block has reached the bottom, the wedge has attained some velocity v, and the direction of velocity of the block we don't know. So that block is going to randomly have some velocity in some direction, which I'm going to assume it as two perpendicular components. So one component of the velocity is uh, perpendicular to the inclined phase. Another component of velocity of the block is parallel to the inclined phase. So you can always assume two perpendicular components of a vector. So and now note that from constraint relation, since the block and wedge are always in contact along the common normal line, which I'm just showing it with a line perpendicular to the inclined face, along that common normal line, velocity components of the wedge and the block must be same. So if v is velocity of the wedge, note that v velocity like that, if I take the component along this particular line, that will turn out to be v sine theta. Why is that v sine theta? Because the angle here is theta. So if I take the component like that, that is going to be v sine theta. Now v sine theta should be the component of velocity of the block also along the common normal. So I can simply write this component as v sine theta, and parallel to the inclined phase, I'm assuming the velocity component to be v dash. So I'm taking this variable v and v dash. So two unknowns are there. So we'll write one momentum conservation equation now along the horizontal. So this is just a different way of assuming the velocity vectors. So either way would be equivalently similar. The length of solving doesn't reduce in this particular method in comparison to previous method, but I'm just telling you how we can assume the variables, completely solving it with respect to ground in this case. So we write momentum conservation for the wedge mv towards left. For the block, it is now carefully note, since we have assumed velocity components like this, we have to take the components of both in the horizontal direction. So v dash cos theta and v sine theta's horizontal component over here, this v sine theta's horizontal component will be v sine theta into sine theta. Right, so we are going to get a velocity of the block along the horizontal towards right, that will be v dash cos theta minus v sine square theta. So momentum of the wedge should be same as momentum of the block in magnitude. So we write one equation over there, and then energy conservation. Now energy conservation for this entire arrangement, mgh will be equal to half mv square plus half mv dash square plus v sine theta whole square. So why I have written like this, kinetic energy of the block is going to be two perpendicular components. So it is speed will be root of v square sine square theta plus v dash square. So kinetic energy becomes this term for the block, and kinetic energy of the wedge is half mv square. Now you can solve these two equations, get rid of v dash. So from equation 1 you get v dash and put it in equation 2 wherever v dash is there, and then solve for v. If you solve for v, you get the exact same expression that you got in the previous case. You will get this expression, root of gh divided by secant square theta plus tan square theta. So see, if you had made a mistake just by applying energy conservation for the block that is sliding down and wrote mgh equal to half mv square, see, that is not that is another kind of caution, that the energy for a system of two moving objects you cannot conserve only for one of the moving objects. So one mistake that could happen is simply writing mgh, drop in potential energy of the block, equal to gain in kinetic energy of the block. Well, that is absolutely not going to be true, for the reason that here there are two moving entities and the block is going to influence the motion of the wedge. So when you're going to have moving entities, you have to always conserve the energy of the arrangement as a whole when there are no non-conservative forces. So obviously here there are no non-conservative forces, so we are conserving the energy of both the moving blocks put together. Well, yeah, so that's about this particular discussion out here.